Today we'll continue these geometric type, describing these geometric type problems. One thing that is going to come up actually maybe in a couple of weeks in the class is the concept of an analytic center. It's actually not an analytic center of a set, although people informally say the analytic center of a set. They don't mean that. What they really mean is the analytic center of a set of a description of a set, which is a set of inequalities, right? So, and the analytic center goes like this. Let's say we have, the equality constraints we just keep right here. But suppose we have a bunch of inequalities here, right? And what this means, we look at, so obviously, the fi of x should be less than 0. Minus fi of x is what people would call the margin. Typically when that's positive. So minus fi of x is the margin. And it's roughly, how much you have left before you violate the inequalities. That's the margin. And the so-called analytic center of a set of inequalities is given by minimizing the negative log of the, this is the margin, minus fi of x, right? Another way to say it is you maximize the product of the margins. Okay, so this comes up in a lot of other things, in log utilities. It's used universally in networking and things like that. So this is not at all uncommon. Okay, so that is the so-called analytic center. Oh, of course, that's a convex problem. Why? Because minus log minus argument is convex and increasing. Okay, and then the fi's of x are convex. Okay, and this is, we'll actually we'll see very soon that this is actually quite straightforward to compute. Matter of fact, you will actually be you'll be writing code that will basically compute analytic centers and things like that. Okay, so that's the analytic that is the analytic center of a set of inequalities. And here's just a picture of what it looks like for a polyhedron, right? So this shows you what's feasible. Each of these corresponds to one of the rows here, each of those lines. The dashed curves give you the level curves of this log barrier. This is called the log barrier. It's called a log barrier. I think that's maybe borrowed from physics or something like that, because it's like a potential function that goes up to infinity as you approach the boundary, right? So that's like a barrier for a particle or something like that, right? If that were an energy. Okay, and a couple of things you can see. It's actually kind of cool. So we've marked there the analytic center. That's the point where that barrier is minimized. So whatever that point is, it maximizes the product, actually, of the margins for the inequalities. Okay, so that's what it does. And you can see actually that the level sets, close down to the analytic center are actually, of course, going to be very close to ellipsoidal, right? That's of course true for any kind of smooth any smooth function, right? So this is the dark ellipsoid drawn there is this. It turns out that for the analytic center, if you calculate the Hessian of it, then the ellipsoid defined by the center, but with a 1 on the right-hand side, that ellipsoid is guaranteed to be inside the set. Okay, so we'll talk, this will be important later. If you puff that ellipsoid up by a factor around m, actually m would be enough because that would be square root of m squared there. If you puff it up by a factor of m, then you cover the ellipsoid. So basically it says that the ellipsoids defined by analytic centers also have this approximation property, right? That, it gives you an inside ellipsoid, and then when you puff it up by a factor, it covers the set, right? So it gives you this approximation. Here, the approximation depends, now remember that for things like the Lohner-John ellipsoid or the minimum volume, covering ellipsoid or the maximum volume inscribed ellipsoid, there it depended only on the dimension. Here it depends on m, which is the number of inequalities here. Right, so if m is much larger than n, this is a worse bound, worse approximation bound of a convex set. So, okay, but anyway, this you'll be seeing much more about this in a couple of weeks. Okay, What we're going to look at now is linear discrimination. Probably most of you have seen this maybe in some basic machine learning class. But here's the problem, and there's many variations on this, but it looks like this. I'm going to give you a set of points, x1 through xn. These are vectors and a bunch of y's. And if you like, these are simply feature vectors associated with a positive outcome and a negative outcome in some kind of Boolean problem, right? So I have some data. And what we seek is a hyperplane. So that's defined by a vector A and a constant B. And we want all the xi's to be on one side of that hyperplane, and we want all the y's to be on the other side. So that's what we want, separating hyperplane. Actually, shockingly, this was studied in the early 1950s. People came up with something called the perceptron algorithm, which you might have seen somewhere. It's like a very early thing. And weirdly, many years went by before someone looked up and said, dude, that's an LP. In which case, people literally down the hall know how to solve these, right? So it's just one of those cases where the diffusion of knowledge had, it took some time. Right. So there is a subtlety here that we're going to look at. One thing we have to be careful of is the notation, right? So here, the variables are basically A and B. And the data are the xi's and the yi's, right? Which violates this usual convention, right? That things at the end of the alphabet are typically your variables, and things at the beginning are typically your parameters or data. Okay? So you have to be on your toes here. So what sort of inequality on A and B is this? What kind of function is A transpose xi plus B? What kind of function of the pair AB is that? It's linear. Yeah. Okay, that's linear. Okay. Now there is one thing here. We have these strict inequalities. Okay. So let me just say a little bit about that. There are a lot of cases where strict inequalities are silly and just mean nothing, and you just quietly replace them with inequalities. Okay? So here'd be an example. You're working with someone and they're designing a power amplifier, and they go, your budget is 50 milliwatts in your design. And you go, cool, okay. And then they come back and they go, it's strict. You have to be less than 50 milliwatts, not less than or equal to. And it's like, okay, this is just completely idiotic and makes no sense. Everybody see what I'm saying? So you just quietly try to explain to the person that doesn't make any sense, and you quietly replace less strictly less than with less than or equal to, and no one gets hurt. Everyone got this? Okay, so that's fine. Now, if we try that here, let's see what happens, right? So you'd say, well, AI transpose X plus B is bigger than or equal to 0. And I also want A transpose YI plus B less than or equal to 0. Anybody got any suggestions about how to solve that system of inequalities?
A and B 0?
A and B 0. I like it. So A and B 0 works. Okay. So this is one of those cases where the distinction between strict and non-strict actually matters. Right? It actually matters because when you make it non-strict, it's got a silly solution which is uninteresting. Right? Okay. So in a lot of these cases, you actually have to hand argue each one. I'm not aware of a general principle. Okay? You hand argue each one, and I'll do that argument right now. The main arguments go something like this. That inequality is homogeneous, right? In other words, if I double A and B, then whatever this is, which is supposed to be positive, goes up by factor 2, right? Everybody agree? Same over here. Right? For this one, same for the other one, right? If this is supposed to be less than, if I double A and B, these things are negative. Whatever they just got twice as negative. Everybody following this? So what I could do is, my claim is that I can without loss of generality replace these strict inequalities with these non-strict inequalities with a 1. And the way I do that is up here, if you give me an A and a B that satisfies this, I simply scale them by whatever factor is needed to make, however positive that was, how negative that was, I multiply by a factor which makes that bigger than or equal to 1. Everybody got it? So that says if there exists A and B that satisfy that, then by multiplying them by a positive number, they're going to satisfy this. The converse goes like this. Converse is relatively straightforward because if I tell you a number is bigger than or equal to 1, it's definitely positive, right? So everyone got this? It's actually a subtlety. It's actually quite important, and I don't know. You could easily encounter this. That was actually both in research or other things or other places. So this is something we kind of expect you to know about. Everybody, yeah.
Is there anything stopping us from saying A transpose X plus B is greater than 1,000,000?
Nope. It's fine. That's totally cool. Yeah, yeah. So if you want to put 10 to the 6 here, and minus 10 to the 6, that's perfectly good, right? And then to be quite precise, what I'm saying then is the first set of inequalities are feasible if and only if these are feasible, if and only if your variation where 1 is replaced with 10 to the 6 is feasible. And they're all, if 1 is feasible, all of them are feasible, period, right? And if 1 is infeasible, all are infeasible, right? And how do we translate among them? We just scale them by various things, right? So like if I have an A and B that satisfies these and I want to satisfy yours, I just multiply A and B by 1,000,000 and then they'll satisfy it. Does it make sense? So okay. All right, so so we did it very quietly, but I did it with just half a line saying they're homogeneous in A, B, but I just gave you the full argument for why that's the case. Okay, all right. So actually, what does this say? Oh, sorry, we can go back. This says that if you gave me a pile of vectors, one set of vectors and another set, and you wanted to know, can you separate them with a hyperplane? And the answer is it's an LP feasibility problem. Right, that's what it says. So it means that's immediately tractable, right? We could just solve this, okay? Okay. Well, we could do more. You could do things like this. You can actually say, well, now that I know that there is one, I might want to pick one of these separating hyperplanes, right? And one way you might do it is something like this. If I have two hyperplanes like this, like that, and they're normalized with a 1 on the right-hand side, or minus 1. The distance between them is 2 divided by the 2 norm of A, right? You can just calculate that, right? In fact, this is a slab, right? So this middle thing, this is A transpose X plus B equals 0. This is, it doesn't really matter, but this is either, let's say, the minus 1, and this is plus 1, let's say, right? So that's what that is. And the width of that slab is going to be 2 over the 2 norm of A, right? By the way, what kind of function is this? Convex, concave? It's a trick question, but a perfectly good one, I think. Like, what kind of function is that of A? What do you think? The answer is it's neither convex nor concave. I was just messing with you. I just wanted to see if anyway, it's fine. It's not, right? So, okay, it's nothing, right? So if you say maximize this, it's not concave, that's for sure, okay? Yeah, you can picture it in your mind if you want, right? In R2, the norm, it's got level curves like this, and that thing is a function. It's a crazy thing with a weird pole, right? It's 0. It goes up to infinity. So it's definitely it's not convex and it's not concave. Actually, in some directions it's convex and in others it's concave. So, okay. All right. Doesn't mean we can't maximize it, right? Because maximizing this is the same as minimizing 1 over it because it's positive, right? So that says this problem is convex. That's a quadratic program. And that is, if you solve this problem, this QP, you'll actually get the thickest, separating slab. Make sense? Right? And in fact, we can even say a little bit about there's an interesting way to get that slab. So for this problem over here, I think this shows you the separating slab for these points and these points, right? Does all make sense? Okay, and let's see, that's a QP. Again, you have to be very careful because you have to see what the variables are and all that sort of stuff. Here the variables are a and b. Xi and yi are data. Okay, so that's like robust linear discrimination is the way you might say it. That's dialect. That's like machine learning, old school machine learning dialect. Okay. Now it's actually kind of interesting to take for this problem to work out what is the dual of this QP. It's not a QP. Sorry, I misspoke. It's not a QP unless you square it. That's an equivalent problem. That's a QP. This would be, I guess, an SOCP, right? But I think that none of this would matter. Okay. So if you work out what the Lagrange dual is, you get something that looks like this, right? You have these two sets of inequalities, and you end up with something that looks like this. You should maximize 1 transpose lambda plus 1 transpose mu subject to, and you get something that looks like this. It's actually kind of interesting, right? And it says that the sum of the lambdas and the sum of the mu's have to be equal, right? And you get something like that. Okay, and the optimal value of that top problem is actually the maximum margin of separation, right? It's the norm or whatever it is, right? Okay. So if you stare at this long enough, you realize that we can actually, what we can do is change variables to normalize the lambdas and the mu's. They're both non-negative vectors, and we replace them with vectors that sum up to 1 and are non-negative, otherwise known as mixture coefficients. So we do that, and you plug that in up here, and various things happen, and you end up with this problem here. And now this is very cool because now we can look at it, right? This says that theta is a set of mixture coefficients, and so this is a general point in the convex hull of the original x's, right? Because it's a mixture of them. This thing here, again, these are coefficients that are non-negative, add up to 1. This thing here is actually a general point in the convex hull of the yi's. And what this says is you should minimize t subject to this norm less than t. Obviously, it's the same as just minimizing this thing. This is the epigraph formulation, right? And then this, so what it's really saying is very geometrically clear. It says minimize the distance between 2 points. One is in the convex hull of the x's and one in the convex hull of the y's. Does that make sense? So it's actually very cool. So if we go back here, it says the primal basically says expand, find the thickest expand a slab until it stops fitting between the two sets. The other one says form the convex hull of the dark points in your head. Just do that right visually. Form the convex hull of the white circles here, and then find a point in the 2 points in those two sets which are closest to each other. And sure enough, you're going to get something like, I don't know, probably that dark point and then a point over there. Just all make sense? Right? So it's kind of, it just means that a lot of these geometric problems, duals are interpretable. Duals are usually highly interpretable and kind of interesting. I mean, it doesn't help you do anything. It doesn't solve it better, blah, blah, blah. But it's just sort of interesting just to see that it all makes sense. Right? So, okay. I think we looked at that. And now we get to something that's actually, well, useful. So here it is. Now what it is you have points that are not linearly separable, right? And again, if you've had a first course, maybe in the first 2 weeks of a machine learning class, you would have seen this. This is like the so-called, it's getting close to the idea of the support vector machine, which we'll get to in a minute. But what you do is you add, and this is in the style of how it's described in a machine learning class, which I think is poorly, but that doesn't matter. That's fine. And so what you do is you say, well, look, I can't satisfy these inequalities. And you go, cool, I'm going to give you some slack. That by the way, that parsed both mathematically and colloquially, right? So what it means is, instead of requiring these things to be bigger than 1, I'm going to say they're bigger than 1 minus UI. UI is non-negative. It's your slack. It's how much we're going to shrink the requirement on the constraint so you can satisfy it, right? And then we're going to say something like, let's minimize the sum of the slacks. Like how much do you actually, how many inequalities do you actually need, do I need to give you slack on so you can satisfy them? And you'd get a problem that looks like this, right? And it's actually quite interesting here. We would do it, we would write this in a very simple way, but that's okay. But okay, and it turns out this is actually kind of useful. This is now, it's a heuristic for minimizing roughly the number of misclassified points, which I can show you what that would be. Actually, why don't I show you that? So here's what it would look like. Let's see, I will write down, let me see what it is. It's, let's take AI, so this is AI transpose, A transpose XI plus B, right? We want that, here's 0, right? And if I ask you whether you have misclassified a point xi or not, the question is whether this is negative, right? So if you're going to misclassify, that's a problem, that's something that looks like this, right? That's a cost, right? So if I took this function of these, I would actually, what I would end up getting is precisely the number of data points I misclassified. Everybody agree with that? And because if this is negative, it means I wanted this thing to be positive. Or okay, here I can, here, if you insist that's positive, I guess I have to make it like that, okay? Right? So that's what it is. Now this function, of course, is not convex, so you can't minimize that, right? Then what this says is you should actually do something like this. You should say, I want that to be at least 1. And then your cost function, the cost function we have looks like this. Because it's the amount, and actually it's super interesting, it makes perfect sense. That's equivalent to this problem here. That's these numbers up here, the U's and V's. So that's convex. And it's actually super interesting to think about what it means. Here's what it means. It says that if you have a data point, and we think of 1 as the margin, right? So it says, you know what? If you classify correctly with at least, over here means you classify correctly, bigger than 0. If you classify correctly with a margin of 1, more than 1 or more, then that's cool. There's no cost. Like you did fine, right? You start charging over here. We're actually charging for classifying correctly, but being less than the margin we desire. Everybody following this? Okay. And then it just grows linearly, right? So, and actually you can see something immediately, which is this function is bigger than this other function. And so it turns out that the optimal value of this is actually an upper bound on the number of misclassifications. So again, if you're following this, that's great. And if you aren't, that's probably okay too, right? So, okay, everybody, all makes sense? So, how many people actually have seen things like this in a machine learning class? I hope a fair number of people. Good, okay, good. Okay, and then all you do now is you add, I guess they would actually square this probably up here. They would square this thing. And then this trades off 2 things. This will trade off the 2 desirable things. Number 1, having small slacks. Small slacks corresponds to this surrogate function. In fact, there's a whole way to view this which makes perfect sense, which is someone says, find me a hyperplane that misclassifies as few points as possible. And you go, cool, the function looks like this. And you go, I can't do that because it's not convex. Then you'd say, well, I'll use this convex function here. Makes perfect sense, right? And you say, I'll minimize that. Everybody following this? Anyway, by the way, that story often, in many, many fields, that story usually has a very good outcome, right? That someone says, I want to do X, and you'd say, can't do that, not convex. Then someone says, but here's like a surrogate, which is convex. And then people observe it to work really well in practice. Usually about 5 years later, somebody writes a theory-oriented paper that basically says, actually, you never even wanted to solve the first thing, which you can't solve anyway because it's a bad idea. What you really wanted to solve was the convex relaxation. So I won't go into details on that, but that comes up many, many times. Like, I mean, here's one in finance. People would say, at at with 99, what is my whatever my 0.99 value at risk? That's how much money could you lose, in a 1% event, right? That's value at risk. By the way, it's used universally throughout finance, banking. It's written into regulations, everything. So some people figured out a very cool thing called conditional value risk, CVAR. If you don't, you don't have to know what these are. That's actually kind of that for value at risk. It's exactly the same thing, right? It's a convex surrogate for value at risk. Everybody following this? Okay. It's convex, and that means we can do all sorts of stuff. We can analyze portfolio. We can construct portfolios that have constraints on CVAR and all sorts of. Everybody got it? Okay. 10 years later, people analyze it and find out that the value at risk is what's called an incoherent risk measure, and CVAR is not. So they write down some axioms. I mean, again, this is just the story, right? You write down some axioms that a risk measure should have. And what it means is that value at risk is actually, it's actually just a bad measure of risk, right? And too bad that it's what all banks use, many hedge funds. It's written into regulations, right? So it tells banks how much money they have to have on hand to avoid a run on the bank and all this kind of crazy stuff. But anyway, so that's a perfect example where the convex thing turned out to be actually what you really wanted to do, not the one that sounded the most natural in the first place, right? This is another one. It turns out, here's an incredibly bad idea, is to say, I have a bunch of data. Please find me a separating hyperplane that separates, that misclassifies as few as possible. But that sounds completely reasonable. Anybody would say that, right? It sounds reasonable. It turns out it's not. Something like this is actually much better. Yeah.
In this problem, does it matter if we choose like plus minus 1 as the
as the margins?
Yeah, exactly.
No. It doesn't. It's not going to make any difference at all, right? You can make them 10 to the 6 if you want, right? And actually, what would happen is just everything would just scale, right? Because actually, if you look at it, everything's homogeneous, including the objective this way, right? So everything would just scale. Wouldn't make any. If you don't like 1 as your canonical positive number, choose another one. You can make it E just to mess with people, or pi. You can make it square root pi. Just that's not a bad idea. Just to do that, so that somebody poking through your code later goes like, "Whoa, what is that?" Yes.
What do you mean by homogeneous?
Homogeneous means that if you multiply the arguments or the variables by, in this case, by a positive number, then that expression value goes up by the same number, right? So a norm is a great example, an absolute value, a norm, right? And you can see here that the variables are like A, B, U, and V. And if I multiply them all by 2, you tell me what happens to the objective. It goes up by 2x, right? So it's homogeneous, right? So that's the, yeah. Okay. Everybody got this idea? Okay. Well, you can actually do, this is people in machine learning, you describe this as kernel methods, but we could just do this, right? Suppose you want to separate 2 points by some nonlinear function, right? Now, of course, there's a gazillion functions that separate 2 sets of points, because I could actually define a function that's positive right around each of our x's, negative around each of our y's, right? And then I don't even care what it is anywhere else. It doesn't matter. It's a half. I don't care. Or 0. It doesn't make any difference, right? That's silly. You want some family of functions or whatever to regularize your choices. And so, you could do things like this. We can make so f of z contains these basis functions. And then theta is now a linear combination of basis functions, right? One of them, by the way, could be 1. That would be a very common basis functions. And then what you want to do is you want to find these inequalities. Now this looks complicated, right? Because maybe somebody in these things, there's like sines, cosines, hyperbolic cosine. I mean, who knows what's in those? There's, some weird things. I have no idea. Maybe those are like weird radial basis functions. It doesn't matter, right? But it'd make you nervous. But the point is, that's data. And so these are just vectors. They're just constant vectors. And it's exactly the same problem, right? So, okay, that makes sense? Maybe an even simpler interpretation of this is even better and really dumb. You think of this as, I would think of this as feature engineering, which is like, thanks for your x's, thanks for your y's. I'm going to put them through some functions. Maybe I get a bigger vector, and you say, now just do support vector machine on that, or separate them that way. That's another way to say it. So, okay. So you could do crazy stuff, like you could say, I want to do quadratic discrimination. So to do that, you set up inequalities that look like this and this, and the variables here are p, q, and r. What kind of inequality is this and this in p, q, and r? Yeah, they're linear, right? Because the left-hand side is actually linear in the triple p, q, r, right? I mean, and you have to get used to this because you see x transpose px, and you immediately want to ask, you know, it is quadratic in xi, but xi is data, so it's not a variable. Your variable's p, right? So that's what it. And you could do crazy stuff, like you could say, you know what, I want to see if I can separate some data by an ellipsoid, right? And that would just be that would end up being an SDP. You'd have an inequality constraint. You'd have a matrix inequality constraint on P, something like that, right? And this would be like a separation by an ellipsoid. Somebody want to name a use for that? So I give you a bunch of data. Some is, let's say, maybe these are like good outcomes or something. Maybe these are bad ones. So anybody want to?
Location.
What's that?
Location.
Yeah, I mean, it could be, it could be that you have some incredibly complex industrial process. You set your knobs various ways, and you run the process, and you get a bunch of data that looks like this. These are the ones that came in, these are the product that came out up to spec. This is the one that failed, right? And so what this will do is it'll give you an ellipsoid in the original space that tells you if you set your, this is where you want to set your, this is how you want to set those values, right? And you get, you know, an ellipsoidal safe set or something like that. That make sense? Okay. And then you could do very weird stuff like, here, we've separated these points by a quartic, right? I mean, but anyway, you get once you get the idea, you can do anything you like with it. Although you have to admit, it looks kind of, well, okay, I'll try one for you. I give you a set of points, some x's and some y's, and I say, I'd like you to separate them by a minimum degree polynomial. I have to tell you what the degree of a polynomial of x and y is, but let's say it's the maximum. A polynomial has got, you know, it's a sum, it's a linear combination of xi to the pi, you know, yi to the x to the pi, y to the pi, qi. I'm going to take p plus q as the degree. Okay, so someone tell me, can you solve that problem? And what kind of a problem is it? How do you minimize the degree of a polynomial discriminator for given data? First of all, could you do it? Yeah.
Just iterate.
Yeah, by iterate you mean try degree 1, otherwise known as a hyperplane. Fail. It's a fail. Then you say, I'm going to try quadratic. Fail. Cubic. Succeeds. Then you're done. That was your algorithm? I like it. Perfectly good. Is it anything else? We have a name for it. That's just quasi-convex optimization. Because the degree of a polynomial is actually, it's a silly one, but it's a quasi-convex function, right? Because I list out all the coefficients. Let's just do it for one variable. I list the coefficients of a polynomial, and the degree is I look along the vector for the largest coefficient that's not 0. That's actually quasi-convex. Okay, so just to, you can just go on and on with these things. You'd probably write a paper about some of these things. I mean, hilariously, but actually, almost certainly. It'd actually probably be better than a lot. Anyway, okay, I'll stop right there. Okay, so our last topic is called placement and facility location, and this is just there's a whole bunch of problems that look like this, right? So It typically goes down in like 2 or 3 dimensions, right? But there's cases where it goes down in higher dimensions, right? And the way it works typically is some of the positions are given and the others are variables. And then for each pair of points, I have a function that's a function of the two points, the 2 locations, right? I mean, actually, in many cases, they're 0, meaning it doesn't really matter. And then you just want to minimize the sum of these functions that are functions of the 2 locations, right? And, you know, there's a lot of interpretations. So, I mean, the famous one, I think it's called like warehouse location problem or something like that. And it basically says, what you do is you have a bunch of facilities, I and J. Fij is the transportation cost between the 2 facilities. And that might grow, I don't know, it might be linear, it might go quadratically or something. It doesn't matter, it's something. And then some of the locations are fixed, and then you want to choose the locations of the others so that this total cost is minimized, right? Your total transportation cost. This is kind of universal in circuit design, right? So what happens there is, I don't know, you have any of the many chips in my phone and your phone, all your electronics would have little cells. I mean, this goes down at many levels, but let's do it at the gate level. So you might have, I don't know, 10 million gates, right? Each gate is connected to, you know, order of magnitude 3 or 4 others, right? Roughly, right? I mean, some have, you know, big fan in, some have big fan out, but mostly they're connected to like between 1 and 3 others, right? Or actually, I guess 2 and whatever, 4 others, something like that, right? Then what you want to do is you want to choose where these gates are going to go, and you want the ones that are connected to each other to be nearby. And there, you would actually take this thing, the cost. This is 0 if cell I and cell J are not connected to each other. And this would simply be something like the L1 norm if they are, right? The L1 norm, because when you run wires on a circuit, you don't run like this. You go this way, and then you go through a via to another layer, and then you go that way, or something like that. Everybody got that? So this is kind of like universally used, right? So, okay, so that's an example. We'll look at some examples here. I mean, just a baby example, just so you can visualize it. And here, by the way, the idea of designing penalties and functions just comes up again. So here it is. I guess these ones on the boundary we imagine are fixed points, right? In a circuit, those would be like something that you've already settled on, or it could be something like a pin. You'd say that's where the external pin comes in. It's locked down. That's where it is. That's where that comes from. And then you're placing these things, right? So let's see what they are. Let's see if this makes sense. In this first case, so what we're going to do is we're going to minimize. So, and the lines here show you, it's a graph, and it tells you which things are connected to which others. Okay? And what we do is on every one of those, we take the distance, in this case, the Euclidean distance between the 2, and we take a function of it. So if we literally just minimize the Euclidean distance, we get this thing here, like this. Okay? So whatever this is the arrangement of those 7 or whatever black dots in there in such a way that the total length of all of those edges is minimized. Everybody got that? Now we minimize the sum of the squares. By the way, this is silly. That's this is in a linear algebra class. Because it's just a least squares problem with equality constraints, and that's gotten analytical. So it doesn't matter, right? But that's what that is. And what happened? They got more spread out. And I'd like someone to explain. Using kind of, just anthropomorphize it. So why would that happen? Right? By the way, this is the 4th power here. So, and they get spread out even more. Somebody, yeah?
The longer lengths in the first one got penalized more because it's square.
You mean in this one?
Yeah, well, compared to the first one.
Sorry, yeah, in the first one, basically you would, if you're going to explain this cost function, you'd say it's pretty chill compared to squaring the distance, just taking the distance is pretty chill about long lengths, right? And so sure enough, you get a bunch of long lengths. right? In the second one, it's way less chill about that, right? That's what you're going to say?
Yeah, and smaller lengths. Like,
Exactly. So, yeah.
It's chill about the.
Yeah. So and then this one is chill about big long lengths, but it still cares about small. So it actually has an incentive to push things together even when they're pretty close. This one here, this is square, and so what that means is doesn't like long lengths at all because you square the length. Short distances are actually okay because short squared is like real small. Everybody, right? Everybody got this? Okay. And so once you see that, you understand kind of all of this. And then I have a question for you. What would you imagine if I used the following function? Did I write it as h of, I did. Okay. So h of u is going to be, I'll just draw it if you don't mind, 0, some distance d, and then that. So suppose it's dead zone linear, like that. What does it mean? If I did that, if I did placement with that function, what it would say is, you know what? If you're within distance d, like, I'm totally cool. And actually, I don't get happier if you put things even closer than d. Everybody got it? Okay? And I would like to know, what do you think would happen if?
A lot of values get pushed to d if they're above d.
Exactly. So a lot of distance values would be kind of at d, right? Just heuristically, right? Because basically it says, look, the incentive to push things closer, once you get within d of someone, it's a neighbor if you have an edge. Once you get within d, this thing doesn't care anymore. And you might as well just go work on other stuff. Go find things whose distance is bigger than d and work on those, right? I mean, I'm completely anthropomorphizing it, but that's what makes sense? So actually what's cool about that is the placement problem gets hard, non-convex, when you add one more extremely realistic constraint. And it's this. I'll just mention this because if there are people here who actually do circuits or stuff like that. So a more realistic placement problem is something like this. Each of these things actually is like a cell, right? It might look like this, and this one looks like this, right? And maybe the xi's are the center. And an extremely common constraint is that they don't overlap. I mean, kind of duh, right? So that constraint is non-convex. Everybody got that? Here's what's cool. If you do this, that's actually a pretty good convex heuristic for getting a layout where things are at least d apart. Everybody got this? And I could actually tune this. If these were squares, I could make for each edge, I could make d equal to one of the diameter of the radius of this one plus the radius of that one. And in that case, it's a heuristic, but I will tend to get things that don't overlap. So, okay, but make sense? Yeah, okay. All right, so that's placement. Okay, so this actually finishes a whole section of the course that was on just sort of applications. I mean, it was just kind of a whirlwind tour. You're encountering a bunch of other applications in your homework. So, and I think the idea is just to see a whole lot of these in different fields, different areas, how it works. And then also know about, I mean, of course, in the homework and watching these things, I'm telling you what the problem is. But one of the things you want to be thinking about is, like, if you encountered a problem, how would you set it up so that it would do something that you wanted to do? I mean, which is kind of the idea behind designing, penalty functions and things like that, right? So, okay. Now, the next part of the course is actually going to be on how do you actually solve problems. So that's going to be the next course. The next section of the course. It's actually, and we'll probably have a small bit at the end where we'll actually do some other interesting applications, but this is important, so we'll do this first. So we're going to talk about how, what happens when, let's say, you call the solve method in CVX pi, right? I think actually we had discussions about what what happens at the highest level. At the highest level, what happens is it takes your problem and it transforms it. Just, you get an equivalent problem, and then you get another equivalent problem, and another one. And you reduce it through a chain of equivalences until you get to some standard form we can solve, like a linear program, quadratic program, or second order cone programming, or semi-definite program. Okay, so that's the first one. We're actually not going to talk about that, although it is super interesting, but it just uses the ideas from the beginning of the class of a reduction of equivalent problems. So we're not going to talk about that. That's what CVXPy does. Now the next section of the course is like, how do you solve an LP or a SOCP or a semi-definite program? That's what we're going to look at. And there it's also, we're going to work our way up. And the way that's going to work is we're going to start with, at the very basics, with just linear algebra. So, how do you solve linear algebra things? And we're going to, then you'll see that we'll start with that. On top of that, I'll show you how to solve, let's see, we'll show you how to solve quadratic problems. Oh, by the way, solving quadratic problems, that's linear algebra. Then the next step up, this is just to give you the big picture of what we're going to do. By next week or 2 weeks, then we'll say something like, okay, we will solve your non-quadratic convex problem by solving a sequence of quadratic problems. But solving a quadratic problem is linear algebra. And then the stuff we're going to talk about right now comes into play. And then we'll go above that, and eventually we'll get to interior point methods, which will handle constraints and everything else all this way. So that's the big picture. Okay, so what we're going to do is going to go all the way down to the bottom. Well, we're not going to go to the gate level or anything like that. We're going to go to the floating point level, right? So at the floating point level, so we're going to talk about numerical linear algebra background. Actually, honestly, I think everyone needs to know this. I'm just going to give you a little tiny bit. There's an appendix on this in the book. Please read it. Actually, just because this is useful for, this is useful. Anyone here, if you do anything that has anything to do with math and computation, like anything, which is, pretty much, if you're in this class, you're in that category, right? You need to know this. And to me, it's completely unacceptable to not know at least a bit about how linear equations are solved. And I'll tell you why. Because, for example, you're going to learn crazy things. Like, we'll see cases where on my phone, I can solve a set of linear equations that's like 1,000,000 by 1,000,000, right? So you need to know what's easy, what's hard, and all that kind of stuff. And it is not intuitive until you have seen this material. Some of it is not obvious at all, okay? So that's the big picture. And so we'll start just by talking about, matrix structure and algorithm complexity. Suppose we want to solve a set of linear equations, right? Like ax equals b here, right? So we want to solve that. If a is like for general methods, it grows like n cubed, right? And I should mention something about this. In theoretical computer science, actually, the number's not n cubed. Does anyone here know what the current number is? Somebody here's got to know. Go ahead. By the way, I wouldn't know. So if you say the wrong number, it's totally fine. I know the range it is. What is it?
I know it's between 2 and 3. I think it's like 2.4 or 2.6.
Yeah, okay. It's around 2.4, maybe 2.3 something. I have no idea.
The record just got broken by Google because they use reinforcement learning to come up with a faster algorithm.
Awesome. So it's what, 2.3 now?
I don't know, somewhere around there.
Okay, yeah, okay. It's 2.3, right? So into the 2.3. Now, these are, that is fascinating, right? Because it can't be less than n squared because you got to look at all entries of the matrix, right? So you might imagine, how could you do this without, sort of n cubed? Anyway, you can. It turns out those algorithms are utterly and completely useless in practice. Completely, right? Maybe sometime in the future they won't be, but right now they're just useless, right? Super interesting. And weirdly, the methods people use to show that low complexity in theory are actually extremely close to the methods people use to make solving these things fast in practice. So I will say what that is shortly. And that part is not obvious at all. So the idea is super useful, but the actual results are utterly useless, right? Those. Okay, back to this. So what's cool is if has got some structure to it, then you can actually solve this a lot faster. Like, I mean, here's like a no-brainer. What if I told you A is diagonal? Right? Then you're like, yeah, I know how to solve AX equals B when A is diagonal. And you go, but I said, what if A was 1,000,000 by 1,000,000? You'd say, yeah, I can do that in about 300 microseconds on my phone. Everybody see this? And you go, but how would you store 1,000,000? And you go, well, that's the point. I'm only going to store the diagonal entries, so I'm not going to store the ones that are zero. Is everybody, okay, I mean, that's an extreme case. I think most people would get that. A profoundly stupid case, but there's going to be others where it is not obvious at all, right? So, and we'll get to those. Okay. All right, so here's how this works, and it's really cool. The history is very cool. It goes back to the 60s, maybe even earlier. So a floating point operation is, it's like an addition of two floating point numbers, subtraction, multiplication, or division. The truth is that's a big old lie, because I think a division takes something like 8 times as long as an add or something like that. But like this is just for order of magnitude. I'll also say other reasons why all of this model is completely wrong, but it's fine. It's good enough for this. Okay, and some people got weird in the 60s, and they decided a floating point operation was actually a multiply plus an add plus some indexing work. And you're like, okay, whatever, right? So, okay. So here's what you do is you look at an algorithm that does stuff, and you count the number of flops as typically polynomial. There might be a log in there, which people a log is just like, you just change it to a constant, right? Because that's what it really is in practice, right? So you express as a polynomial function of the problem dimension, and you simplify, you only keep the leading terms, because this is very crude, right? So it is not remotely a good predictor of computation time on modern computers. And this is just changing. It's getting all very weird and all that kind of stuff, right? I mean, this should be kind of obvious, right? Okay. But it's useful as a rough estimate of complexity. And a lot of people divide all these things in their head into various groups like that. So the way, and this is also historical. So vector operations are ones that take like two vectors, right? And you have an inner product. What does that take? Well, I have to multiply xi by yi for each, so that's n multiplies, right? Then I have n minus 1 adds, because I have to add, the x1, y1 plus x2, y2, and blah, blah, blah. Okay. So, basically inner product, people would just say n. I mean, the 2 is silly, so you just say n. The sum would be the same thing. It's just like n flops. And by the way, these have very cool names. That's also a retro name. So if you know this, you can impress people. So this is the first one. This is called BLAS, BLAS level 1. Second is called BLAS level 2, and that's BLAS level 3. BLAS is basic linear algebra subroutines. That's from the 1960s. Okay. So this is, but it's actually a very good distinction to be thinking about, right? Okay. So let's, and then by the way, I mean, some of this persists, but gets like really crazy when you start looking at things like GPUs. And, God help you if you are looking at TPUs. But anyway, so on GPUs, they're like crazy optimized for this, right? So there you can just get like just insane speed, right? So anyway, well, I'll make some mentions of that later. And these are things like you should know, right? Like if you're in the middle of, if you're putting something together, and you'd say you can't multiply like those two matrices together. You should step back and say, oh, that's BLAS level 3. And I think our friends at NVIDIA have a really good idea about how fast. I think we can do just fine, thank you, right? So, okay. All right, so you can also look at the numbers here, right? That BLAS level 1 are kind of linear in the single dimension, right? BLAS level 2, if you're going to form AX, right? Matrix vector multiply, that's going to be, it's like basically MN, the product of the two. And let's see. Yeah, this is fine. I mean, if things are sparse, it gets very interesting. That's a structure everyone should know about. So sparse, how do you calculate the inner product of two sparse vectors? And how, roughly speaking, how much does it cost? I'll give you two vectors, each dimension 100 million. They're sparse. Each one has 100,000 entries. You tell me. I want the inner product of the two. How long? What does it take? How do you do it? Also, I want to know what the flop count is. It would, yeah. What do you do? Go ahead.
You cycle through the non-zero elements.
Yeah. What you do is, the only time you ever have to do anything is when there's an entry that's non-zero in both vectors, right? So the absolute, here's a big upper bound on the number of flops it could take, right? It's the minimum of the number of non-zeros. Everybody got that? Of the two, right? So that's an example. Matrix vector, same story, right? If A is sparse and I multiply by a vector, that's going to be you're going to have a whole lot. It's going to depend on capital N, the number of non-zero elements, right? Okay, and there's other structures, right? Like what if I gave you A as a low rank factorization, right? So suppose I gave you A as a million by million matrix, which you can't store. But what if I gave it to you as the product of a million by 20 matrix and a 20 by million matrix, both of which I can store on my phone, right? Then how do you multiply? How do you actually form AX in that case, right? Here would be the wrong way. You would do, this is the absolutely wrong way, right? This would be, what am I multiplying it by? X, right? This would be a very poor idea, right? Because the first thing this would do is try to attempt to allocate 100 million by 100 million matrix, and then it's game over. Everybody following this, right? But this is just silly. I mean, no one would do that. That's the right way, okay? Right? And then this one, you just, you work out what it is and so on, and then work out that one, right? So that's another very common structure is low rank, right? So, okay. All right, that's good. Okay, this is the idea. So this is blast level 1, 2, and 3. These are the different levels. By the way, there's some very interesting things. The complexity of matrix multiply, these are n by n matrix. Again, our friends in theoretical computer science, it's like 2.35 or whatever. It's the same number. If Google figured out a better number, that's awesome, right? Good for them, right? Everybody got that? And it's, it's fine. Actually, I can tell you how that works because the exact same method is used in practice. So I'm going to show you that just for fun. Not the details. Actually, maybe almost all the details, but it doesn't matter, right? So if you multiply if I'm going to multiply two matrices, right? And this is like A, B, C, D, like E, F, G, H, something like that. So what you do is you just partition it into blocks like this, right? Okay. And you can work out what it is, right? Like, I forget what these entries are. This is AE plus, BG or something goes here, right? And so then you have a recursive method that says you just recurse down, and each of these is given by blocks as well. Everybody following this? All right. And now comes the smart part. So now first we're going to do some theoretical computer science, and that is somebody figured out how to work this out with 7 matrix multiplies, not 8. Because your naive method would use 8. They did it with 7. And now you just recurse down. And you're going to get a number that it's not going to be n cubed. It's going to be n to the 2.8 or something like that. Everybody following this? Okay. Now let's see. This is actually how it works entirely in practice. And this is your friend. By the way, normal people do not need to know about this, right? But it's good for you to know about it. So the way you multiply two matrices, so it depends, right? Let's just actually, we can even do this, just first let's do single thread, right? So single thread is going to work like this. By the way, if you multiply these out, you don't use the silly 7 multiplies versus 8. It's just 8 multiplies. So if I say, take your matrix, chop it up into subblocks, chop those into subblocks, and then just write a recursive thing and go. Then someone says, how many flops do you end up doing? And the answer is n cubed. So it's the same as if you just wrote a one-line, C program that said, walk across the first one, down the first row, and fill them in, that kind of thing, right? Everybody follow me this? So you'd say, you haven't changed the number of flops. Like, how on earth could this be faster? Again, anyone want to suggest something? You'd have to know a little bit about like computer architecture and how computers work, but I feel like all of us should know a little bit about that. Yes? Yeah, that's exactly right. It's cache optimized, right? So what you do is the bottom, the lowest level in the hierarchy are, 16 by 16 matrices, right? Why? Because you can multiply 16 by 16 matrices, directly at the lowest level of cache, right? The next group up is like, 256 by 256 matrices. You can multiply 2 of those using your level 2 cache. Everybody following this? So, by the way, this is from the 1960s. 1970s? No, maybe 70s. Okay, let's go with that. Everybody following this, right? So it's actually completely stunning what happens when you do this right. Oh, and by the way, the same things go to a world where you have a lot of cores. So this could be a GPU with 10,000 cores, right? And you say, oh boy, is it good at multiplying? I can multiply, 5,000 16 by 16 matrices by other 16 by 16 matrices all together in like 2 microseconds. Everybody following that? Right. So there are people who work on these things know exactly what those things are. They know exactly what they can do. And so then it's the same thing. You'd chop these things up into these things. And all of us are utterly unaware of this, right? Which is kind of cool. But we benefit like crazy, right? So everybody following this? So if you ever meet, I don't know if people even do, well, there are people who do this, like in my department in CS. So anyway, if you meet one of those people, just like, remember I told you if you meet someone who works on like devices and things like that, you should thank them. If you meet someone who works on the lowest level stuff like this, thank them too. Because they're the ones that allow the rest of us to use like NumPy and SciPy, for that matter, Torch and things like that, because it's just awesome. Like what they've done is amazing. And we're the beneficiaries. So, okay. All right, so if you didn't follow what I was saying, that's okay, but you should kind of know about this, I think. Let's talk about like speed of like current, computer and things. So you could actually do things like, you can do it yourself. And you can actually do some of these calculations and make guesses about how long something's gonna take. Or you could actually say it did that calculation at this number of flops per second, right? And by the way, so anyway, somebody tell me what's here, I don't know, this is a 4-year-old laptop. What will this do for, I don't know, matrix vector multiplies and stuff like that? Anyone? By the way, here's a hint. It's measured in gigaflops, which is 10 to the 9 flops per second. Right? So what would be a speed number? You either know this or you don't, but what would be a speed number for like a 5-year-old laptop? Any, how many billions of flops? By the way, that's a lot of floating point operations, just for the record. But how many billions can you do in a second on like a how about a newer computer? What's the number? Anyone know the number? Range? Okay, it's between 1 and 10 for this. It could easily be 30 for this. Why? Because people who know what they're doing have like optimized matrix multiply, because people do it a lot. Okay, what would it be on a simple GPU? Well, I have a GPU in here for my graphics. So, what is it there? Now we're talking 100 easily. That's a baby GPU. And on a real GPU, you start getting towards the teraflops, and then it goes up from there. Everybody, by the way, these are just amazing numbers. And we're the beneficiaries, right? So, just as a quick thing, how long does it take to multiply like 2,000 by 1,000 matrices? Or someone want to? Look, it's order n cubed flops, so that's 10 to the 9. So someone tell me the number. That's a gigaflop. That's a billion flops, how long does it take? I mean, I could just do it right now, but I'm not going to because I know what would happen. But go ahead, somebody tell me, what's the number? Does that take a minute? You'd say, wait, do you realize? Like multiplying 2,000, each of those major, I'll make it sound crazy. You'd say, you have 2 arrays, each of them have 1,000,000 numbers in them. Everybody following this? And then you have to multiply them together and they all connect with all of them? And you're going to do 1 billion multiplies? That's crazy. Everybody following this? So how long does it take?
100.
What's that?
100 a second.
That's about right. So it's on the it's put it this way, it's measured in milliseconds. Yeah. So 100th would be on a new computer. Okay. So this would be a tenth of a second. This would be 100 milliseconds here. So it's probably worth sitting down and like seriously pondering like how amazing that is. And there's a lot of people to thank for that. Right. So anyway, so if you're whatever, if your roommates or neighbors or something do this kind of stuff, you should thank them. So, okay. Does that sound good? Oh, and what about on a super high-end GPU and I'm multiplying 20,000 by 20,000 dense matrices? You'd be terrified is the answer, is what it is. It's unbelievably fast, right? Okay, but actually that's not the main point. We're going to be talking about other stuff where you don't need a supercomputer to achieve things. You just need to be smart. And that's going to be the theme of the next, of the material we're going to look at. Okay. So we're going to just build up real easy and just say, let's look at some linear equations. When is it easy to solve linear equations? Well, here's one time. If it's diagonal, that's idiotic. Like it's order n. Okay. What if a matrix is, what if it's lower triangular and you want to solve it, right? So you want to solve something that it's lower triangular. So it looks like, A11, A21, A22, right? A31, A32, A33. I'm not going to draw the zeros, right? Times, let's say X1, X2, X3 equals like B1, B2, B3. And this, you probably saw this and probably even in high school or something, right? So how do you solve this? Well, look, the first equation is A11, X1 equals B1. So X1 is B1 over A11, right? Now you know X1. The second equation is A21, X1, but you know what that is. You already calculated it. So the second one is, A22, X2 equals B2 minus, A21, X1, which you already know. Okay, so that method is called forward substitution because you solve for x1, then x2, then x3, then x4, and whenever you have one, you're gonna substitute it in future equations. Everybody got that? And when you work out the complexity, that's going to be actually n squared flops. Okay, so that's cool. By the way, it's different from n cubed, right? So that's, in fact, there's a factor of n in there, right? So you already know something. It says that if you had to solve some triangular equations, you can do that like really fast compared to just solving non-triangular equations. Okay, and if it's upper triangular, you do what's called backward substitution. It's the same thing. In that case, you get xn first, then xn minus 1, and so on, right? Oh, and by the way, this is not how it actually works. This is blocked. That's how they actually do it, right? So there's little blocks. Again, we are blissfully unaware of this, but when you solve a triangular system, they don't do it line by line like this. It's actually blocked, right? So, but we can pretend it looks like this, and the conclusion is the same. Okay. What if a matrix is orthogonal, right? Like, then it takes 2n squared flops, right, to compute A transpose, to compute, A inverse B, right? Because A inverse is A transpose, and then it's matrix vector multiply. So actually, that's what it was. Okay. There's lots of other cases, right? If A could be, here's a very famous structure for a matrix A. It's identity minus rank 1. I think that's called maybe a householder reflection, or somebody might know. Somebody in ICME or something could tell me. I think that's right. That's called the householder reflection or something. Those, again, you can solve in n flops, right? Because you just are smart about how you do it. And the storage is also clear. You would store U, not the matrix, right? A permutation matrix is a good example, right? If you have a permutation matrix and you want to know how long does it take to solve, like, a permutation matrix times x equals b, you just unpermute them, which is the transpose. And you actually don't even do any flops because all you're doing is you're just moving numbers around, right? So permutations is kind of hilarious because if you ask under a flop count analysis from the 1960s or 70s, it's 0 flops. Because you just move, it's actually like mem copies, right? You're just moving numbers around, right? Of course, in fact, that can take a lot of time on if it's a vector that's 100 million high or something like that. Okay, all right. So these are examples, and now we're going to get to what the method is. And actually, it's much more important to just understand the high level idea than the low level details, right? Except if you're in the few people who actually work on these methods so that the rest of us benefit. But the rest of us, here's the method. It's actually very simple, and there's already like immediately weird things that I don't know, some of you probably will leave today knowing something you didn't know before that's weird and shocking. So here it is. The general method works like this. You take a matrix A, you want to solve AX equals B. You take the matrix A, and the first thing you do is you factor it. And factor it means you write it out as a product of matrices. You know a bunch of these factorizations, probably. Like there's the QR factorization, there's the eigen decomposition, singular value decomposition. You probably know a bunch of these already anyway. So, all right, so you factor it into a product of matrices, each of which is easy to invert. People say that. By the way, when they say that, that's slang. It doesn't mean that anyone's going to invert that matrix. When you say easy to invert, it means it's easy to solve AX equals B. Right, that's what they actually mean by that. But they just say easy to invert, even though no one is inverting any matrices, right? Okay. So this is really, really quite dumb. It just says, well, if A is this product, then the inverse of A is the product of the inverses in reverse order, right? So I get this thing. And now I just put parentheses the right way, which is to say I first put a parentheses around the first one, A1 inverse B, and I calculate that. So it's actually, what you do is you solve this to get x1, right? That's actually that second expression. Then I have to multiply by A2 inverse, which I do by simply calling the solve method on A2 with right-hand side x1. Everybody see that? So in fact, you solve this by just a sequence of solves. Everybody, you can even think of this in a beautiful object-oriented way where each of these things has a solve method, right? And solve literally means solve A, B means it returns A inverse B, right? Some of these methods are idiotic, like it would be diagonal or a permutation or something like that. Doesn't matter. That's the idea. So you solve that by literally just a sequence of solves. That's it. Okay? All right. Now, usually the way this works, there are exceptions, which we're going to talk about, but it works kind of in a cool way. Usually, in the simplest, most generic cases, the factorization costs order n cubed. And then we'll see that the solve actually is going to take order n squared. Now things get weird. Because suppose I ask you, how long does it take me to solve one equation with 5,000 variables? So 5,000 by 5,000 matrix A, 5,000 vector B, and I want to compute, whatever. I want to actually factor A, right? Well, okay. It's order of magnitude. Yeah, it's under a second. It depends on what you're doing it on, but it's not minutes, it's not milliseconds. That's order. Well, it'd be milliseconds on some crazy things, but that's fine, right? Everybody follow this? And now I'm going to ask you. Let's say it's a second. We'll make it simple. Suppose I say, well, no, now I want to do this. I want to actually solve 10 sets of equations with the same matrix, but different right-hand sides. Well, the naive method would take 10 seconds because you just have a little loop or whatever, unless you had 10 cores around and parallelized it, but that's okay, but whatever, right? So it'd take 10 seconds. Everybody following this? How long, in fact, does it take if you know what you're doing? Let's review, right? So I want you to solve 5,000 equations, 5,000 variables, right? Takes a second, okay? Now I'd say, okay, thanks for doing that. I'd like to do it now for 10 sets with the same coefficient matrix. A normal person would say, like 10 seconds? I mean, are we, right? And what is the actual number? It's 1 second, right? Why? Because, you know, if it's 5,000 by 5,000 matrix took a second to factor, solve is going to be a factor n smaller because that's n squared, not n cubed. Okay? So it takes, so the answer, that works out to actually microseconds, right? So the answer would be, oh yeah, it's about 1 second, plus maybe about 150 microseconds. Everybody following this? Okay, so how many, is it weird? I mean, until you know this, this is not obvious, right? So actually, how many people knew that basically you can solve 10 sets of linear equations, basically the exact same cost as solving one? Some of you must have known this or something. Okay, everybody, okay. I'm not detecting that you're that impressed. Are you like what is are you just like, who cares? Or, I mean, what? It's kind of, I mean, it's kind of cool, right? Okay, I'll put it this way, I'm impressed. I think you should be, honestly, I think you should be too, right? By the way, this requires you actually know what you're doing, right? Because if you actually just, if you say, you know, for right-hand side in right-hand sides, you know, solve AB, you're sure. By the way, there's another name for this is called factorization caching, right? So it means you factor once and then do multiple solves, okay? All right, everybody, I think this makes sense, right? Okay, and you know, the most common one is the LU factorization. L is lower triangular, U is upper. And it basically says you can take a matrix A. If it's non-singular, you can write it as a permutation times a lower times an upper triangular matrix. The cost of that is like n cubed flops. And then this is how you'd solve it. It looks like this, right? So this one dominates, right? And then these things, this is the solve method, right? This is where you're actually walking through there's three factors, that's why there's three things here, right? Each of these is solving essentially or computing it's working with the inverse of one of the factors, right? And so this is what you're doing here. And this whole thing here is order n squared. That's order n cubed, okay? So, and this comes up in a whole lot of areas, but okay, so this is cool. And this is kind of the same as the Gaussian elimination that you were almost certainly tortured with either in high school or undergraduate days, right? So it's basically this. Yeah. By the way, when you were taught that, did anyone say that it has nothing to do whatsoever with how people actually solve equations? Probably not. No. So, yeah, so why you would cause people to actually do Gaussian, I mean, I don't know. It's like writing an assembly language program. A person should do that either 0 or once. And absolutely no more than that. And most normal people should do it exactly 0 times. But they should appreciate, oh, sorry, we need a very small number of people who are very weird and like that to do that. That's all they do, right? So that the rest of us can benefit. That's kind of the way this all works out. So, yeah, so why, anyway, so this is basically the same as that. Except it's not the way it really works. Of course, the way it really works is all of this is the same thing, except all these things are blocked, right? And if you're on if you have multiple cores, like on a GPU or just multiple cores, stuff is being done at the same time, right? But other than that, the idea is identical. So, okay, so I think we'll quit here and we'll continue next time.